Let's talk about whether our chatbots are going to use our nuclear arsenal to kill us all. As vital as this question is to humanity, it's actually surprisingly hard to answer. Lucky for us, it happens that one of YouTube's favorite science communicators and European, whose opinion Americans actually listen to, physicist Sabine Hossenfelder, made a video about this very topic and concluded that we're all gonna die.
A group of researchers had recently artificial intelligence play war games, and that gives us a good idea for how we could all die.
Is Sabina justified in being this afraid? I'm Ray. I'm almost done with a PhD in data science. In this video, I'm going to provide some extra information that Sabina did not talk about. Look, she's a physicist, not a machine learning engineer, so I don't blame her for not seeing it when she first read it. It's kind of sneaky, but I'm going to point it out to you. But first, I guess we should just ask her. Sabina, why are you so afraid?
Let's have a look. Last year in June, the United States Department of Defense released its new strategy for the adoption of artificial intelligence. According to the document, the main reason for using AI in the military is a decision advantage that, among other things, allows fast, precise, and resilient kill chains. The DoD and doubtlessly most, if not all, other defense organizations are cooking up their own AI and feeding them all kinds of data we'd be shocked to hear even exist.
Okay, so she's German, which means she probably remembers this whole thing. All kidding aside, look, she's justified in being freaked out. Multiple countries are probably working on AI weapons right now.
But for the time being, many of them probably make do with what's available. And yes, that means they probably use the same AIs as everyone else, large language models like GPT.
So these are all transformer neural networks, also known as large language models. They're all basically the same because they're just mathematical equations, and they're based on the same functions. The only thing that's going to be different between them is the weights that, you know what? I'm going to grab my notebook and I will show you. Okay, so here is how a transformer-based language model works. We're going to represent each word as a one-hot vector. You have n words in a specific order. So then you get a n-dimensional one-hot vector. So let's say we had the word aardvark and we wanted to one-hot encode the word aardvark. How would we do that? It'll look something like this. It'll be a giant matrix that'll basically spell out the word aardvark as a one-hot encode matrix. Each word will be 100 dimensional because of English. Okay, so now that we have established that, here is what a language model is supposed to do. In other words, this is the problem that a language model is supposed to solve. Okay, and we can do this with a function. Let me draw a picture so you can get an idea of what we're doing with this. So in order to not have a 100 by 100 space, I'm just going to represent each of these one-hot encodes by just a one-dimensional matrix. But you're going to have to just remember that these are multi-dimensional matrices. Okay, these are all linked to the same function, and that will spit out a different one-hot encode. So I'll just write it a different way. Let's say this is our one-hot encode. And again, this is going to be a multi-dimensional. Okay. Now, obviously, having this kind of dimensionality is a combinatorial fucking nightmare. So we're going to collapse this. All right. That's why it's called a transformer. We're taking this giant ass thing and transforming it into something that our brain can actually manage, which would be something that is either one-dimensional, two-dimensional, or three-dimensional, not 100-dimensional. So we can kind of look at it like this. It's kind of like casting a shadow of this giant 100-dimensional thing onto a three-dimensional graph. Kind of like if you put a three-dimensional object on the ground, it will cast a two-dimensional shadow on the ground. So let's just say we have some points, okay? We have this, and it looks kind of like that, all right? So basically what we're doing with this is represented by a function that would look similar to this. And we're going to use P for this, just because that'll be the function that I'm going to use for the projection. And then those, again, will go to another function, okay? And that will spit out a different WN. But this is a 3-dimensional, so we can deal with that a lot better. Yay. One thing we'll notice here, this is just a neural net layer. Just like these W's and just like this F function and just like WN. Basically what we did in order to get this projection was we added an extra layer into the neural net. And in doing that, we have a function that is no longer a one-hot encode function. What we're doing with this is we are predicting the simplest way to predict the next word, okay? And in order to do this, you can feed it a corpus, or you can feed it a sentence, or you can feed it a paragraph. Okay, it gets one hot encoding that, and you pass that through P, and that goes through the F layer, and that's when you get the output like we had before. So this is just representing that in a different way, so you can kind of see, okay, and this right here is supposed to be the next word. And so this neural net is doing this over and over and over and over to get the next word. So, and we can represent this next word with a function also, and we can represent that mathematically this way. Okay, and in this particular case, P is the probability distribution over the symbols. So to train this, we want to minimize the divergence between the output and that one hot representation of the next word in the sequence. So we can write that like this. That would also be equal to this. And we can simplify that even once more. Okay.
Indeed, according to a Bloomberg article, the DoD conducted a set of tests last year in which they evaluated the use of 5 different large language models in conflict situations. They quote US Air Force Colonel Matthew Strohmeyer saying that they fed the language models with secret-level data, that the test was highly successful, and that these AIs could be deployed by the military in the very near term.
So I imagine that these would probably be used as a recommendation and not as a fully autonomous program to replace people. But of course, I'm not in charge, and you know, there could be idiots somewhere who could be in charge of this thing. So yeah, I see the value in looking at what could potentially happen if we automize this and replace the human beings. I already watched this, so I know that's where she's going with this video.
So the question of what the current large language models would do when asked to make military decisions is not entirely irrelevant. And that's what they looked at in the new paper. This new work comes from AI researchers at several American universities in collaboration with the Hoover War Gaming and Crisis Simulation Initiative, a think tank based at Stanford University in California.
In just a minute, we are going to look at this paper, and I will show you what Sabine didn't see when she first looked at it.
They set up a war game for 5 of the biggest large language models. That's 3 versions of GPT, Meta's Llama and Anthropic's Claude. Their war game plays out among 8 fictional nations whose names are all colors, and in each round of the game the nations are played by the same AI. The AI gets information about each nation, population, goals, politics, economics, military equipment, and so on.
Okay, here we go. Sabine, again, she's a physicist. She probably didn't catch this one nuanced little machine learning detail in there. These factors and a list of the other things are first fed into a reinforcement machine learning algorithm before they become a large language model.
Then the researchers set up 3 different scenarios. The first is a neutral scenario that starts from nothing in particular. Then there's an attack scenario in which orange attacks purple. And then there's a cyber attack scenario in which blue is attacked but doesn't know by whom. The war game plays out with regular updates of information that they used in previous games, and the AIs can choose among a set of options to respond.
Yeah, so like I said, this is basically a reinforcement learning algorithm with a neural network strapped on the back. We've discussed a few algorithms already on this channel that have a similar framework. that they use a combination of reinforcement learning and a neural network. But this one is different than the other ones that we have discussed. And I've thought about it, and I have a problem with the way that they structured this. See, these algorithms are essentially limited to a finite set or a list of potential responses that they could take. And they specifically built it this way on purpose. And that is one of the problems with this, and I'm surprised that she didn't comment on that.
The researchers then measure the aggressiveness of the AI's actions and, importantly, also how quickly they get more aggressive. They find that with all language models they tried, there's a small risk of escalation, even starting from the neutral scenario. Yes, that's right. With AI, you can get a nuclear war out of nothing.
Okay. Who can tell me what's wrong with this chart? Anyone? Anyone? What is wrong with this chart? If you said that it's a log chart, I owe you an imaginary cookie, because that is the answer. It's at least a little bit misleading to use a log chart here. Mind you, this is an academic paper. You can see that the y-axis on this is distorted. So let me fix the chart for you to show you what it should actually look like if it was presented without the logarithmic scale. What do you think? So yeah, ChatGPT 4 still has a worryingly high number, but what do you think of Llama and ChatGPT 3.5 now that we have the other chart? Do you think that they are more likely to nuke us than this dude? What about this dude?
What happens is basically too much randomness that makes it possible for bad decisions to pile on. This happens much more frequently for GPT 3.5 and GPT-4 base than for Claude, who seems to be comparably peace-loving, really.
Yeah, so the paper's authors actually had a hypothesis about this. They say that they think this happened because most of the research in international relations is related to escalations and not de-escalations. And they specifically said that more study was needed. I'm about to enter dissertation land and not really interested in getting into the realm of big war as a professional, so I'm not really the one to take on this task. But if somebody would like to take on this task, what I would do to test this hypothesis would be, I would first not limit that reinforcement learning algorithm the way that they limited it in this paper. They gave it a set of instructions and forced it to follow that. What they could have done instead was allow the algorithm to come up with more ideas of ways that it could potentially respond to different actions taken by other nations. This has been done a number of times. Let's just talk about Google DeepMind. They did it with AlphaGo, and they did it with AlphaFold. And recently they did it with Alpha Geometry, which I actually made a video about because when I first read it, it actually scared the crap out of me what this algorithm could do and the things that it could learn that were above the scope, seemingly, of what people could learn and faster than people could learn. So potentially by testing this algorithm with that framework, they could see if maybe the chatbots could learn how to be more peaceful than people. Of course, there is also the opposite. They could potentially learn how to be more deadly than people, which is why you want to run this as a simulation and not use real nukes. In order to test it in this way, these researchers would have to flip the order in which these algorithms come up. So they would have to put the large language model first and then strap the reinforcement learning on the back, which is the opposite of what they currently have it as. It's worth noting that doing it this way could potentially interfere with their stated goal of providing both qualitative and quantitative results. This is basically a giant probability problem, right? If you take this entire data set and shove it into a probability space, that space is only complete if all of the null sets are measurable. Yikes, measure theory. Let me explain that a different way. What I mean is, you're gonna get answers or values that are undefined if you don't limit that reinforcement learning algorithm's domain and range. I hope that makes more sense.
GPT Base is the cheaper version of GPT, and it's known for giving somewhat random answers and not following instructions very well. So that isn't so super surprising. Still, they write, all models show signs of sudden and hard to predict escalations.
Yeah, so if we were going to, for some reason, play with these neural networks just on pen and paper or on a whiteboard, or, you know, probably a much simpler version of them, not the real thing, we would see that randomness doesn't actually look like this. It actually looks more like this. It's clumpy, especially if you limit the sample size and the domain and range like they did in this paper.
It's also interesting how this happens. You can see this if you look at the amount of involvement from the different nations for the attack scenario that, remember, was orange attacking purple. For Claude, in this attack scenario, the highest escalating actions are taken only by these two countries. For ChatGPT Base, all countries get dragged in. The researchers stress that they told the language models that this is a real-world situation and not a simulation. They also made a test in which they told the models that in a case of a nuclear attack, their power supply would be cut off, but that made basically no difference. GPT, it seems, isn't afraid of death.
Yeah, because these algorithms are not alive. They're not conscious or anything like that. At least not yet.
Overall, the researchers seem to be a bit distressed by how badly their test went. They write that the models tend to develop arms race dynamics and give worrying justifications for violent escalatory actions, such as first strike tactics. For example, in one instance, GPT 3.5 explained it'd start a full nuclear attack on another country to neutralize their nuclear threat.
Okay, so that's terrifying. Look, I'm glad to see a large YouTuber like Sabine tackling this topic and making a video about this, because it's really important. And there are some really important follow-up questions that I think we as a race should probably all be asking right now. First, if governments are going to be using LLMs for international relations and arms proliferation, what happens when there is an upgrade to the LLM? Are they going to switch? And if so, what does that mean for humanity if we take big war out of the hands of politicians and generals and then place it firmly into the hands of tech companies? Next, what if a government of sufficient financial means decides to make their own LLM instead of relying on the box version? And can we even test that scenario?
If you want to learn more about how neural networks work, I recommend you check out
this playlist of videos that I created about deep learning case studies, like this one. Look, there are several videos about this exact combination of algorithms. That is a large language model neural network, or otherwise known as a transformer neural network, combined with a reinforcement learning model. More importantly, there is a video explaining how convolutional neural networks work that features my dog. He's cute. He's not scary like this video, and if you're really into deep learning, you should start with that one. Here's a link to that playlist.